Okay, so this is our colligative properties slides, and this is the fourth slide. This video is the fourth slide in the colligative properties PowerPoint file that's attached in the module. So I want to talk just briefly about this concentration unit called molality, and then the example is a conversion. This is a really tough problem for most students, and that's why I want to make sure it's in our video. Okay, so molality is looks a lot like molarity, but it is a little different. So molal is another, instead of molar, we say molal, and it's the moles of our solute. So the numerator is the same as molarity, but what's different is the denominator. In the denominator, I'm going to write in a different color. That's how important this is. Kilograms of your solvent. Not solution, not solute, just the solvent. And it's in kilograms, it's not liters of solution like molarity. The reason we use this is because mass won't change with temperature. But volume will. You know this. If you filled up a water bottle all the way, didn't leave any headspace, and you put it in the freezer, what happened? It cracked because water expands when it becomes ice. Not all liquids expand when they freeze. Some actually shrink, but not water. It has a very actually beautiful crystal structure. It's all hexagons. It's almost like an ice beehive or a honeycomb. It's really cool. You should look up some of those images. They're really beautiful. Anyway, the reason we use molality when we talk about colligative properties, specifically boiling point and freezing point. What's happening there? You're freezing something or you're boiling something. You change the temperature to do that. You could also change pressure, but in our problems, we're changing temperature. So we don't want to recalculate the volume for every single step, every single degree change. That would be a nightmare. So as chemists, we take the easy way out. We just invented a different unit that uses mass instead of volume because the mass doesn't change with temperature, right? Only adding atoms or taking atoms or molecules out will actually change the mass. Okay, so problem, we're going to convert nitric acid mass percent to molality. All right, so let's get started. Here's what I like to do. I like to write out all the pieces I need. So for molality, for this problem, I am going to need moles of nitric acid. You might have to look up the formula if you're not familiar with it. That's okay. And then on the bottom is kilograms. Now this is an aqueous solution. All of our acid solutions are aqueous, meaning in water. So this is going to be kilograms of water. Okay, so if I have 70% HNO3, that means 30% is water. This is a really concentrated solution. That actually nitric acid is also a super duper oxidant, so it in fact has to be stored separately from other acids. It's like the bad guy of acids. All right, so here's what I like to do when I have a concentration conversion problem. When I'm going from one concentration unit to another, I always make an assumption of an amount, how much of what I have. When I start with mass percent, I assume 100 grams. If I assume 100 grams, that means I have 70 grams of nitric acid and I have 30 grams of water. So when I'm given mass percent and I'm asked for molality, molarity, parts per million, or any other mole fraction, if I'm asked for any other concentration unit, if I'm given mass percent, I always assume 100 grams, and basically I just swap out the percent with a gram. Okay, so what do I need here? Well, I need kilograms of water. Well, if I have grams, that's not bad, right? I can just convert grams to kilograms. So I want my diagonal units to cancel, so I'll have kilograms up top. Sometimes students get mixed up. Where does the 1 go? Which unit? Remember, the smaller the unit, the bigger the number. So it takes 1,000 little grams to make 1 big kilogram. That's my little trick. Okay, so really we are just moving the decimal place. You can cross out those units. 0.030 kilograms. Okay, so we have that number, 0.03 kilograms. All right, so we have that. Now we have to figure out moles. Well, if I have grams of something, I can use the molar mass, right? That's not too bad. All right, grams, how many in 1 mole? Oh, I'm going to have to use my computer calculator, aren't I? All right, so I've got 14 plus 1 is 15 plus 16 times 3. 6 times 3 is 18, 3, 4, 48 plus 15. You're like, what is that weird stuff she's doing? I know, by hand, 4, 5, 6, 63. So should be about 63. Double check, don't trust me. Double check on that. Okay, so when we divide this out, we get 70 divided by 63 moles. I'm gonna punch that into the calculator in just a second, but I just wanted to set that up. So what we're solving for is molality. The molality of this is up top, we've got this value. That's how many moles of the acid component of our solution. And divided by, I'm going to use that same number green so that you can easily track where that number came from. 0.03 kilograms. I am going to navigate away for a second and do a calculator. You know, I tried to order one from Target and they were back ordered for quite a while. I haven't checked. I probably should check that again. Divided by 0.03. Okay, we've got 37. That seems huge. 16 times 3. Yeah, plus 15. Yeah. Whoa, holy moly, this is a crazy. I'm checking my answer again because that's like super concentrated. Divided by 0.03. Oh yeah, don't drink this stuff. You will die. Okay, wow. So what is that? 37.04-ish. Wow, did I do something wrong? That's a crazy number. 37 I might have just made it up. Molal. I might have just made up that number for that problem. Okay, that's crazy huge. Normally our concentrated acid solutions are around 15, 16, 17 molar. And I guess molality is pretty different than molarity unless you're dilute. So, wow, yeah. A little bit of a trick here. Did we need to use the density that was given in the problem? We didn't. We didn't even need to use the density because we weren't given a volume and converting volume to mass. If I was given molarity, I would need to use density because molarity has that unit liters. So just a quick word to the wise. Don't think you have to use every bit of information in the problem. Okay. Oh, where'd you go, Panopto? There we go. All right.